没有地方大方式，
Wow. That's an
Okay, again.
Like, I'm
Good
behind.
morning, gentlemen. Today I want to stimulate something new, and before that, a small audio sample. And I think you recognize what this is. This is a screeching door. Everyone knows what it is, but how does this sound? How can you generate such a sound? What's behind that? It's not a classical resonance or something that's vibrating. It's just a repetitive movement, and that's something we want to simulate now. And there is a task in our exercise sheet, which is called the stick slip movement, and which has to do with that. And here we see a body and a spring attached to it, and then we move the spring, and okay, of course, then we have a force on the body. At first, the body will not move because we have Coulomb friction. The block sticks to the ground, and only when we pass a certain limit of force, then this block will start moving. But depending on the forces, it will not move all the time. It will make, let's say, one jump, and then it will stick again, and then it will repeat this movement. Okay, and this repetition that might produce a sound. Okay, so first of all, let us again demonstrate how this happens. Okay, so we have here a block, we have a spring. I start applying the force. At first the block does not move, then it moves, but after some time it should stop again, and then it will move again, and so on. So it's a repetitive movement, and let's think about that conditions. Yes. So we have forces on this block. And one of the forces, of course, is from the spring. So let's move the spring over here. Okay, there is a force because we're moving the limits, the borders of the spring, and that means we have a force here, F spring. Okay, then we have a reaction. That means the block will produce the same force in this direction, but the spring force will also be applied here directly at the block. So everything is this spring force. Then we have two more forces. One is friction. So according here to the surface. And that is always Coulomb friction, but it could be either the static case, that means the block still sticks, or it could be the kinetic case, the block moves. Okay, but in any case, we have here a reaction force, and we could just call it F Coulomb, Fc. And now, let's first here at a reference frame. That means let us define positive directions. Okay, if the accelerating force is to the right, let's also define here positive directions here. So x and velocity acceleration to the right. And because Coulomb friction is a reaction to velocities, we must draw its reference arrow to the left. Okay, and there is a third force. If the block moves, well, then it will feel a force, it will be accelerated. whenever we have acceleration, there is also a reaction to it. And we draw it also in the opposite direction of the actual A. It's also to the left. So this is m times A. Okay, so these are three forces on the body. And now let's go again into the two cases. In one case, the block sticks, and or let's first start with balance. Okay, we have three forces, and that is valid for every case, and that means the sum of these three forces is 0. Let's say Fc and Fc plus m times A minus, because we're going in the other direction, minus the spring force, that is 0. Okay, that's the basic equation, which will develop into a differential equation, and that's valid in any case. But if the case stick, okay, that means we have no velocity. Okay, so that's one condition. We have the velocity is 0, that's the precondition for this case. In that case, we have static Coulomb friction. That means we have no acceleration. Block is just sticking to the ground, no acceleration. We only have this Coulomb friction, and it always has the same value as the spring force. It compensates the spring force. And that we can write, so Fc is the static Coulomb friction, and that always equals F spring, but only as long as we are below a certain limit. It must be smaller than or equal to, well, a certain coefficient, this mu kinetic multiplied with the weight. The weight, okay, it's a normal force, we can also even, so the normal force is m times g, and that's what we use here. So this is the limit, and as soon as the spring force is larger, we will get in the other case, the case slip. And this is defined where we have movement. And in our case, let's say we have only positive velocities. I think that makes sense here. So we can write velocities are larger than 0. That's defined here. So in that case, this Coulomb friction becomes the kinetic variant. Is F kinetic. And this is now always the same value. It is the mu. I'm sorry. Of course, this is the static case. There is a coefficient for static cases. I'm sure all of you knew that. You just wanted to test me if I saw this error. Okay, and in the kinetic case, we have the force which is always the mu kinetic multiplied with the weight. Okay, so the first, that is the limit until something happens. So here, we're here within the stick case, and here obviously my force is smaller than this limit, mu static times the weight. And as soon as we have the movement, then we are at the lower case. So there is friction, and it is the mu kinetic multiplied with the weight. Okay, then more important, we need to solve this equation for the Einstein derivative. That means for our acceleration. So acceleration, or x dot, is then the same as. Okay, let's put these two on the right side. We have F spring minus epsilon, and we have to divide that by the mass. And so we can say we have in these two cases two values. In the first case, of course, when we have no velocity, we also have no acceleration. So we could just say here acceleration in this case is always 0. And in the lower case, then it's given by this equation, but we can enter here just the kinetic ground friction. So here acceleration is s minus the kinetic force divided by mass. Okay. So two cases defined by, let's say, logical conditions, and that is best modeled with a switch. So we will, in a moment, start with that switch. Just one last thought about the spring force. So here we just moved the right end of the spring with a constant velocity. That means the spring force will build up according to spring equals K multiplies the displacement of the spring, and that is the right. Okay, we have here another reference frame. This is x of the spring. Okay, and the displacement is the integral of the velocity. It's the integral. So we have k times the integral of velocity over time, and it's the velocity of the spring. Actually, as soon as the block moves, we need to take the difference between xs and the position of the block. So actually we should use here difference. Okay, let's rewrite it like this. K times x spring minus x of the block. Okay. And here then we also need, in fact, we need the velocity of the spring minus the velocity of the block. So always the differences. In this case, because we know that the velocity is constant on that side, we could just use the multiplication with time. But okay. So I think we have prepared everything, and we can start with the model in Simulink.